Welcome back to the Dargslan networking series. This is lesson 19, and today we're tackling the topic that intimidates more newcomers than almost any other, subnetting. By the end of this lesson, you'll be able to design networks on paper in your head without ever reaching for a calculator. The secret is something I call the binary truth, and once you see it, subnetting stops being magic and starts being mechanical. So here's the roadmap for the next few minutes. First, I'll show you the magic numbers, a trick that lets you subnet in about 30 seconds flat. Then we'll take any CIDR notation and pull out its network address, broadcast, and usable host range. After that, we'll split a 24 into smaller pieces, the kind of thing you do for real departments on a real network. And finally, we'll prove it all works by checking our answers in binary. But before we dive into the mechanics, let's answer the obvious question. Why bother subnetting at all? Imagine you're handed the entire 10.0.008 block. That's nearly 17 million addresses sitting in one giant pool. Dump every device in there together, and you've got a security nightmare and a broadcast storm waiting to happen. So instead, we slice it. Users get their 24, servers get theirs. Guests and voice each get their own. Same address space, but now organized by purpose, better security, smaller broadcast domains, and no wasted addresses. Now here's the trick that makes subnetting feel almost like cheating, the magic number. Take 256, subtract the mask value in the interesting octet, and that's your jump size between subnets. Let's try a 26. The mask is 255.255.192. So 256 minus 192 gives us 64. That means your subnets land on 0.0, 0.64, 0.128, and 0.192. 4 subnets per 24, each with 62 usable hosts. No calculator, no lookup table, just arithmetic you can do in your head. And here's that same magic number trick laid out for every Class C subnet you'll meet in the wild. Notice the beautiful symmetry. As the CDR grows by 1, the magic number halves, the subnet count doubles, and the hosts per subnet roughly halve. A 30 gives you 4 addresses with just 2 usable hosts, perfect for point-to-point router links. And 31 is the clever exception. RFC 3021 lets you skip the network and broadcast addresses entirely to squeeze 2 hosts out of 2 IPs. Pin this table somewhere. You'll reference it constantly. Let's put that magic number to work. With a 26, we subtract 192 from 256 to get 64, so our subnets land neatly at 0.0, 0.64, 0.128, and 192. From there, each block is mechanical. The network address is what we calculated. The broadcast is one below the next subnet, and the usable hosts fill everything in between. So subnet 1 runs 0.1 through 0.62, subnet 2 from 65 through 126. And the pattern just repeats. 62 hosts per subnet, 4 subnets, no binary math required. Now let's formalize that into a repeatable recipe, 5 steps that work for any IP and mask combination you'll ever see. First, find the interesting octet, the one where your mask isn't a clean 255. Second, calculate the magic number by subtracting the mask value from 256. Third, count by that magic number until you reach or just pass your host IP. Fourth, that landing point is your network address. And fifth, the broadcast is simply one below the next subnet, with your usable hosts sitting neatly between them. Let's put that recipe to work. We've got 192.168.1.100 with a 26 mask. The 26 lands us in the 4th octet with a mask of 255.255.192. So our magic number is 256 minus 192, which is 64. Counting by 64s, 0, 64, 128, 192. Our host at 100 falls between 64 and 127. So the network is 192, 168.1.64. Broadcast is 168.1.127, and our usable hosts run from 65 to 126. No calculator, no binary conversion, just 5 clean steps. Now here's the beautiful part. That same recipe doesn't just live in the 4th octet. Slide the mask left and the magic moves with it. A 18 puts the interesting octet in the third position with a magic number of 64, so your subnets land on 0.0. 64, 128 in that third slot. A 12 jumps to the second octet, stepping by 16. That's exactly how 172 on 16, 172 on 32, 172, 48 line up. Find the interesting octet, do 256 minus the mask value there, and count. Same formula, different column. Now, before you start subnetting in the wild, let's head off the traps that catch almost everyone. The big one, 24 does not mean 24 hosts. It means 24 network bits, which leaves 8 for hosts, giving you 254 usable. Always subtract 2 for network and broadcast, except on a 31, which RFC 3021 carves out for point-to-point links, where both addresses are fair game. And when you walk subnet boundaries, add the magic number, not a decimal guess. 192 plus 32 is 224, never 222. Memorize these 5 and you'll save yourself hours. And if you ever doubt the magic number shortcut, here's the proof underneath it. Take 192.1168.1.100 with a 26 mask, write both in binary, and end them bit by bit. A 1 survives only where both sides are 1. What drops out is 192.1168.1.64, the exact same network address the shortcut gave us. The magic number is the speed. Bitwise and is the truth, and they always agree. So let's lock in the 5 moves that turn subnetting into muscle memory. Magic number is 256 minus the mask value in the interesting octet. Subnets march forward in steps of that magic number. The network address is the multiple of magic at or just below your host IP, and the broadcast is 1 less than the next subnet. Usable hosts are 2 to the host bits, minus 2 for network and broadcast. And when anything feels shaky, fall back on Bitwise and it never lies. And here's your 1-page reference for the entire 4th octet. Notice the beautiful symmetry. As the mask grows by 1 bit, the magic number halves, the subnet count doubles, and the usable hosts shrink accordingly. A /25 splits a network in 2, a /26 into 4, all the way down to /30, the classic point-to-point link with just 2 usable addresses. Screenshot this one, pin it above your desk, and within a week, you'll know it cold. And that wraps up Lesson 19. You've taken a fixed-size view of subnetting as far as it goes. Now it's time to break that constraint. In Lesson 20, we tackle VLSM, variable length subnet masking, where you'll learn to carve a single network into right-size pieces for each department, instead of wasting addresses on a one-size-fits-all mask. I'll see you in the next one. And don't forget to subscribe over at youtube.com on Dargslan so you never miss a lesson.